right there. So if someone, for some reason, maybe if my video cuts out, or if you want to come back and review this, I'll post it up on our classroom. There'll be plenty of opportunity. I'm also going to try to post my lecture notes that I have that I'm reading from. I'm going to need to expand them significantly. They're kind of just like a basic sketch of what I want to talk about. And anything I do with my little drawing tablet, I'll try to post as well up on Classroom by Monday, so that you guys have that as a reference just in case you need it. Sound okay? All right. So first things first. This is chemistry, and what we're talking about in chemistry generally is how physical things interact with each other. And I guess the word we have for that is matter. I'm sure you guys have seen in your middle school and previous classes, like some discussion of matter, like the basic parts of it, the history of the atom, right? I was hoping today could just be a nice, easy review for us, since we're still in our first week, of some of those ideas. So if you've seen all of this before, excellent. If you haven't, then great. Now is a great time to start taking notes. You can either type, you can write. I really suggest writing. So why don't we take, I see a couple people have stuff already. Good for you. Awesome, seeing some pens. If you need a minute to go run and get something, take it now. And while we're doing that, let me ask, when I say the word matter in a scientific context, what do I really mean? Does anyone have an idea about what that word particularly means? You can either, yeah, go ahead. That's really not a bad definition, what everything's made out of. It's hard. It's a hard thing to define, right? Because it is kind of everything we interact with on a daily basis, or really in our entire lives. Everything, the air around us, is made of matter. Now, here's an interesting question. Is matter the stuff that we interact with, that we're made out of? Is that what the rest of the universe is made out of? Anyone know? It's actually kind of not. The matter, the stuff that we're made out of, is about like 3 to 5% of the whole universe. The rest of it is like, I think 20 to 30%, 25%, what's called dark matter, which we don't really know what it is. If you ever figure it out, that'll be an instant Nobel Prize for you. So I guess get to work. It's this mysterious thing that well, it seems to have a gravitational effect on stuff. It seems to have a pull of gravity on other stuff around it, but we can't figure out how it interacts with other matter in any other way. It's really mysterious. But even more mysterious than dark matter is dark energy, which seems to be about 70% of the universe. And it's responsible for the accelerating expansion of the universe. And we literally have absolutely no clue what it's made out of, where it comes from, what it does. It is totally mysterious. So again, if you can figure that out, instant Nobel Prize for you for discovering what most of the universe is. So unfortunately, I don't have much more to say about that. Yeah, question. Yeah, so it's not a dumb question. It's actually an excellent question. I'm going to give you a really, really quick version of it here, and if we have time at the end of class, we can go through it much more detailed. Dark matter, we can see its gravitational influence on other stuff, like regular matter, and like stars and gas and dust and stuff out in the universe. We see its influence, but we just don't see it. So we know that there's something there that has a lot of gravity, and we have just no idea. Christian, do you have a question? Very much true. Very much true. It absolutely could be multiple things. And there's a lot of theories about what it could be, and we're just kind of completely uncertain. One big push in particle physics these days, with like big particle accelerators like CERN, the Large Hadron Collider, is to figure out what the heck dark matter is. And there's a few candidate things. If you really want to look it up, there's like supersymmetry, and there's WIMPs, weakly interacting massive particles, and there's all sorts of other crazy things. And the problem is it's really hard to find out. It's a really, really difficult science to measure. Let's see. The way we know about dark energy, as far as I know, not being a cosmologist who deals with like the whole universe, but as far as I know, dark energy we know about because of the expansion of the universe. And not just that, because the expansion of the universe is not just happening, but it's also accelerating. It's getting faster the longer it sticks around. So something is probably causing that, and our best idea is this thing called dark energy. And if you look at the amount of energy it would take in order to make the universe accelerate the way that we see it accelerating, it would mean that 70% or 68%, I think is the actual number, of the universe is made up of this mysterious dark energy kind of stuff. It's a relatively new development in astrophysics. And relatively, I think, like last 30, 40 years, something like that. So, we can go through that in much more detail at the end of class if we have time. I doubt we're going to, but we'll have time sometime this year. So remember that question, and if we ever have a minute. Naomi, you have a question? I figured. I saw her drop out. That's okay. Good thing I'm recording so that she can see the rest of this. All right, so let's start going through this. I'm gonna try to go through this and give you guys some breaks, because boy, it's a lot of talking from me. Give my voice some breaks too. And if you have questions, if you have comments, if you have anything you want to add, please just interject. You can go in the chat, because I'm keeping an eye on the chat, or you can just, unmute yourself. That's fine with me. I'm going to try to take us from, as far as I can tell, the earliest history of the idea of an atom all the way up to pretty close to the modern day. I don't want to get too far into the quantum mechanics side of it, because that can get really complicated, but if you guys are interested, we can talk about it a bit. Okay, so matter is generally, the way that I would put it, is it's stuff. And the idea of the atom really started out, it isn't today, but started out as the idea of that there is a smallest indivisible unit of stuff. Today, we have atoms, which kind of, the word comes from that concept, but atoms are not indivisible. I'm sure you guys know about protons and neutrons and electrons, yeah? So you can divide atoms. You can even divide protons and neutrons. As far as we know, you can't divide an electron. Could be interesting if you could. But the atom still kind of comes to us as like this basic, I guess I would call it a building block of everything around us. So how do we get from this sort of very philosophical idea of a smallest indivisible unit of things, stuff that make up everything, to our kind of very complicated modern theory? The earliest, and I've done a lot of research on this, the earliest reference I can find to something like a concept of an atom comes from India, the 8th century BCE. This guy named Aruni, he was a Vedic sage, and he has this very fascinating theory. I found out about him, and I want to read more because he's really interesting. He has this theory that everything is made of particles too small to be seen, which is true, and they mass together in many combinations into all the substances and objects that we experience. And if you, it's pretty interesting, like, he didn't do experiments to find this, right? In the 8th century BC, they didn't have microscopes or anything in order to do experiments. This was a pure, like, thought thing. He just thought about how the world ought to work and came up with this idea. To be fair, a lot of other people were also thinking about how the world ought to work and came up with some crazy ideas that were not true. So maybe he was just lucky, but maybe he was smart. It seems like from that tradition, another Indian philosopher, and the dates are really uncertain. It could be anywhere from the 600s to the 200s BC. This guy, Kanata, and he's often referred to as the earliest physicist in Indian philosophy. another person who I really would like to read more of. He theorized that every substance you see around you is divisible, but that division can't go on forever. There is a smallest unit, he called it a parmanu, that cannot be divided. He also theorized that it's eternal, and it combines in different ways to make complex substances. If you go a bit deeper into what he wrote, there's some really intriguing, fascinating parallels to Newton, like Isaac Newton's physics, some thermodynamics stuff from the 1800s, and even like some quantum modern physics things. I think it's worth it to read that guy if we can find texts. A quick Googling did not find me any of his original texts, so I need to keep looking. But around that same time, in the 500s BC, the Greeks also come up with the idea of atomism. And this is where most textbooks, I think our textbook, I'm not actually sure our textbook even mentions the Greeks. It might. But most textbooks I've seen start here with the Greek philosophers, even though there are earlier ideas in India and possibly elsewhere. There's two guys most places talk about, Leucippus and Democritus. Leucippus, we know absolutely nothing about him, other than he taught Democritus and the ideas came from him maybe. Democritus, we know quite a lot about. We don't have any of his original texts. We have some fragments. We know that there were about 80 texts that he actually wrote, which is quite a lot, just from other people's writings. And he is credited with the first use of the word atom, or atomos, I guess in Greek, which he said was the basic indivisible unit of matter. And I think one of the interesting things about his particular theory is that he concluded that if there are these tiny indivisible units of matter that he called atomos, there also had to exist between these indivisible units void, is what he called it. We would call it a vacuum today, which is essentially true. It's more or less what is the reality in the world. But other ancient Greek philosophers really did not like that idea of void. So Aristotle, a little bit later, asserted that this is not true. Everything is not made up of these tiny indivisible units that combine in infinite complexity. It's actually, everything is made up of the four classical elements: earth, fire, air, water, in different proportions. And these substances are sort of continuous throughout the universe. They're everywhere. So I think, having read Aristotle when I was a senior in high school, I think I remember he claims that steam is some combination of water and air, but it's like more air, so it rises into the sky, so it can be with the other air, which is a bit interesting. Or like a rock is earth, so when you drop a rock and it falls to the ground, it's trying to be with the other earth. And I think his famous statement is that you cannot inculcate a stone to fall upwards, which essentially means no matter how hard you try, you can't teach a rock to fall into the sky, which is true, but I think he got it for the wrong reasons. And unfortunately, pretty much everybody in the ancient world and the medieval world trusted Aristotle, so this was kind of accepted for quite a long time. A classic example of that kind of thing is Aristotle asserted, I think it was that flies had 4 legs, when clearly if you look at a fly, that is not correct. And people just believed it for over 1,000 years. Like, I guess nobody decided to check. In academics, people just believed what Aristotle said for over 1,000 years without checking. So that, not the greatest record for the scientific method in the ancient world there. And Aristotle is kind of dominant for a long time. In the Middle Ages, there is some idea of atoms in a bunch of different cultures. There's a sort of a tradition of it in India. I think there's an Islamic tradition of it as well. But most of the world, even in those cultures, followed the kind of thinking that Aristotle had, that there's these continuous substances, elements that make up everything. There is one, I guess, notable exception. It's late. It's not in the Middle Ages. It's like in the Renaissance. Corpuscularianism. And you know what? This is a complex enough word. I'm going to draw it out for you. I'm going to write it out for you, I should say. Let's see. I need to share my screens. Here we go. If I can find the dang thing. Oh no. Sometimes I have to click share screen twice for the actual thing I want to show up. There it is. Okay. Corpuscularianism. What? Okay. C-O-R. God, it's a long word. P-U-S. C-U-L-A-R-I-A-N-I-S-M. Okay. And it's kind of a complication on the idea of atoms. The whole thing is, I would say, focused around the idea of corpuscles, which are like, if you're taking Latin, corpus is body, right? Or something like that. I never took Latin, but I know some. So that instead of these indivisible tiny units, everything is made up of these little bodies, I guess, and they're not meaning like little guys in everything. They mean like little blobs that are divisible, but have, different properties. And this idea of corpuscularianism is really closely linked to alchemy. So this is I think this is 1600s, maybe 1700s. And the idea was that corpuscles of mercury could get into a metal and change its properties, from lead to gold or something like that. Alchemy is really the foundations of chemistry, which is interesting. But it's also kind of magical in some ways. Isaac Newton, the famous physicist, basically quit doing physics when in his early 30s, I guess, and focused the rest of his life on alchemy, trying to turn lead into gold and find the elixir of life and all sorts of stuff like that, the Philosopher's Stone, which if you've read Harry Potter, I'm sure you're familiar with. Isaac Newton actually tried to find it. He was a little crazy. One of my favorite stories, if you take Physics 2 with me, I'll read to you from his book about the time that he stuck a knife into his eye just to see what would happen. Well, not into his eye, between his eye and the eye socket, just to see what would happen. He was a little bit nuts. But you know what? He was brilliant. So maybe you need to be a little bit nuts to be brilliant. I don't know. Okay, so corpuscularianism is kind of a little bit of a revival that there's these tiny units that make up everything. It's a little bit off to the side. There's all this alchemy stuff. In the 1660s, around the same time, maybe a little bit later than corpuscularianism, Robert Boyle, who's a chemist, published a book called The Skeptical Chemist, and this is in English when English spelling was not standardized, so I love how it's spelled. This Skeptical Chemist. So if you say it, it sounds like you're talking in a New Zealand accent or something. A skeptical chemist. But in that, he espoused a form of atomism because of a few of the experiments he had done that sort of showed problems with the classical idea of the four elements, the four classical elements making everything up. So he was that's Robert Boyle. I should write his name. I guess it's not really important to know. 1660s. So pretty early stuff. But there wasn't very much, this idea of atoms was, I guess, around still. It was being discussed a bit, but it was kind of underground until the early 1800s. And this is right where most of our textbooks will pick up the story. Let's see. With John Dalton, who's an English chemist, 1808. Who was the first modern chemist or physicist to really accept, and the 1808 is the publication that he did this. Not his, he didn't just live in 1808. That would be remarkable if he was able to be born in 1808 and do some significant science and then die. No, 1808 is his publication about atoms. But he was the first one to like mainstream accept the ancient Greek model of Democritus, specifically of atoms making stuff up. And nobody really knows where he got the idea from. It's not really well documented. He talks about maybe it came from some of his experiments with gas laws, and we're going to talk a lot about gas laws, I think much later in this course, second semester. But gas laws are really important. We'll probably come back to Dalton. But he was experimenting with gases and how they compress and, how they absorb heat and stuff in the early 1800s. And we think maybe some of his ideas came from those experiments, but there's also some, allegations maybe that he just kind of plagiarized directly from some other scientists' work. There's problems with that because this other scientist's work isn't really closely linked to atomism, so Dalton must have had some sort of original insight. But maybe he was plagiarizing things, I don't know. Really hard to say that far back. The next big development takes a while, though. It's Thomson. I guess Thomson's experiments were 1897. He did experiments for which he won the Nobel Prize. He discovered the electron. And I'm going to use the symbol for electron, which is an E with a minus symbol, sort of as a superscript. So the electron's discovered in 1897. That's a Nobel Prize. But in 1904, because he discovered the electron, Thomson comes up with his model of the atom, how the atom works. And so he knew about electrons. He didn't know about protons or the nucleus or anything like that yet. So what he said is the atom is this, basic building block of stuff that has a bunch of electrons hanging out like little bees flying around in this nebulous cloud of positive charge. My pen's going crazy. Cloud of positive charge there. And it's like the cloud of positive charge, I've never been sure with this model exactly what that's supposed to be. I'm not sure what he really thought about that, because it seems like that should be impossible. Just a cloud of positive charge hanging out that's due to nothing. But people call this the plum pudding model. And the idea is that the pudding is this positive charge that's kind of this soup, and the plums inside of it are the little electrons sitting around. Didn't take long for people to realize this was probably dumb, and that's not how things work. Rutherford, Ernst, I think it's Ernst Rutherford, in 1911, just a few years later, did a really interesting experiment. It's called the gold foil experiment. So he got positively charged particles. I'm not really sure how he got them back then, but he did. And what he did is he shot them, little positively charged particles, little pluses, and he shot them at basically tin foil but made out of gold, a sheet of tin foil. And what he observed is that most of the time, these little positively charged guys just fly straight through. Sometimes they deflect a little bit, like sometimes they, curve their paths a little bit, but most of the time they fly straight through. But very rarely, every once in a while, it'll bounce straight back off of the gold foil. And what he concluded from that is that most of the atom, this positive charge, is empty space, completely empty space. That void we kind of talked about from Democritus. But in the very middle is what he thought, and it's probably true, is what he called a nucleus, where all the positive charge is concentrated. So now the model of the atom looks like a very tiny nucleus This is the discovery of the nucleus, by the way. And then around it, sort of nebulously hanging out around it, are the electrons. So, major development, that this positive charge is actually all concentrated into a tiny little area. And if you're really careful with this experiment, you can actually figure out how big a nucleus is by looking at the proportion of positively charged particles that bounce off the foil versus the proportion that go straight through. If you think about it like a target, like here's your atom with the little positively charged nucleus, the area of this part where the electrons are hanging out versus the area of the nucleus, that ratio is going to be the same ratio of particles that bounce off versus particles that go through the foil. Kind of a cool experiment, I think. Pretty clever. And this model didn't stay unmodified for long. Niels Bohr, really famous physicist, 1913, modified this because he was looking at some other very interesting experiments. I'm going to try to go through these because I think it's really important to talk about the kind of experiment he did. We're going to do a little bit of extra thing on Bohr's experiments. But he modified this this view of atoms, of just a nucleus and electrons just hanging out around it, just a little bit. So there's still a nucleus, but electrons exist for Bohr only in these very particular, what are called orbitals. They orbit around the nucleus like little planets. And they're actually restricted. They can only exist in very particular orbitals, which he said corresponded to particular energy levels. So a very low energy electron is down here near the nucleus, and a high energy electron is up here in the higher orbital. And electrons are restricted to only particular energies. And what he called this quantized, meaning that it's not continuous. There's not like a smooth variation of electron energies. The energies are quantized, meaning that they are like just set numbers that they can exist at and nothing in between. Quantized energy levels. And this model of the atom is probably what we're going to be talking about most of the time in this class. We might have some modifications of it. But this word, quantize, is really the root of quantum mechanics. And this is really where it starts. This is really the beginning of quantum mechanics, 1913, with these measurements of quantized energy levels. And I think it's actually worth it in a minute to go through the kind of experiments that he did. But before we do that, I want to kind of conclude the story here. 13 years later, Schrödinger, you probably have heard, I hope you've heard of Schrödinger. Schrödinger, 1926, comes up with pretty much what is still the basic model of the atom today, which is still a nucleus, but there's this sort of almost unmeasurable cloud of electrons in various energy levels surrounding it. And his point through quantum mechanics is that you can't really measure where these electrons are. It's impossible to measure where they are. I hope you guys have heard of Schrödinger's cat, right? The Schrödinger's cat experiment, where you put a kitty cat in a box. I'm going to draw a kitty cat because I like kitty cats. Doot, doot. Kitty cat. And also in this box is a radioactive element of some sort. I don't know, uranium. And if this uranium spontaneously decays, if it's radioactive, if it produces radiation, that radiation releases like a poison gas and kills the poor cat. Oh. But since the box is totally closed and you have no way of observing the inside, you don't know if that radiation has actually happened, and you don't know if the cat is alive or dead. And Schrödinger was saying, well, this is kind of a ridiculous idea. You can't have the cat be alive and dead at the same time. And then if you look into it, quantum mechanics goes, well, actually you can. This is what's called a superposition. So the state where the cat is alive and the state where the cat is dead are both equally true at the same time until you open the box and find out. My college quantum physics textbook had a live cat on the front and a dead cat on the back, which I thought was kind of morbid but also kind of funny. I'm sure I could dig that up and show you guys. I have it somewhere. And in the same way, electrons are in this odd kind of superposition. They could be anywhere around the nucleus. In fact, technically an electron could be hanging out anywhere in the universe, and there's a very small, extremely small probability that that's true. So the idea of different states of being having certain probabilities is sort of central to quantum mechanics as well. Okay, that's as much quantum mechanics as I really want to get into at any given time. How are we feeling? Okay. All right, well, why don't we rock around for a minute, and we're going to come back, and I'm going to take you through the kind of experiment that Niels Bohr was doing that led him to this idea of quantized energy levels. So yeah, let's take just 1 minute. We've got 25 left in class. That's plenty of time. Get a new thing going here. All right. That's about a minute, I think. Let's make sure everyone's back first. Looks like you guys are all here, almost all. I don't think I'm missing anyone. There we go. I've got everyone. Okay. So I thought I would go over the kinds of experiments in general, not the exact experiment, that Bohr was doing that led him to the idea of these quantized energy levels in atoms. So I'm going to draw a big picture of an atom with a nucleus. A nucleus does not have to be that big because I don't really care about it in this particular scheme. What I do need to be big is the energy levels for electrons, because we're going to do some work with them. I'm going to draw 3. In real atoms, there's a lot more than just 3. Okay. So this is kind of our nice mystery atom. So what Niels Bohr was doing is something like it anyway. And we can actually do this in class. We have the materials to do this experiment, which I think is really cool. Is he would put gases, like say hydrogen or helium or what have you, into these little tubes that have an electrical wire running through them. And he would run a really big electrical current through this wire, which would transfer most of his energy to the gas in there. He puts it in this holder. We have these in our classroom, a bunch of different gases. They're called gas discharge tubes. They're actually they're almost exactly fluorescent lights, only fluorescent lights made with very particular gases in them. So if you put a hydrogen tube into this little holder, it'll be nice and pink. Neon is, I think, orangish. You can get various different colors from various different elements. But what he noticed is that when he shines the light that comes out of this gas, so here comes the light, through a prism and splits it up into a rainbow, he doesn't get a nice even rainbow. I don't know how to draw a rainbow with only one color here. There's your prism, though. Like, usually you'd get a whole nice rainbow, right? But if he looks at it, if he graphs the amount of light, so amount of light is the vertical axis, in physics, we would call it intensity, I, and this would be the wavelength of the light. The symbol for that in physics and chemistry both, the symbol for wavelength is a Greek letter. It's a lambda. I don't know why it is. That's the way it is. So if he graphs this, and let's say that, I don't know. Let's say that this side is red, and this side is blue. But if you graph it, the intensity of the light over wavelength, he doesn't get a nice, smooth, even thing like a rainbow. What he actually gets is this weird peaky kind of thing. And he notices, not only does he get this weird kind of peaky kind of thing, he also notices that the peaks are exactly the same for the same element. So every time he puts hydrogen in here, he gets the same pattern at the same wavelengths, at the same intensities. Every time he puts helium, he gets a different pattern, but it's always the same pattern for helium. And what he concludes is that through a lot of work, he concludes that these, he calls them spectral lines, are due to electrons transitioning between set energy levels. So for example, in this little atom here, this energy level, the lowest one for the electron, we would call the ground state. And electrons, what we know is that electrons love to be in this ground state. They love to have the minimum amount of energy in the atom. They like to be chill and relaxed. But if you put energy into the system, they can go to higher levels. Higher energy levels. And what we're doing by running this electrical current through this gas tube is putting these electrons from their ground state into their higher levels. And when they get into these higher levels, they'll hang out there for a little bit, but there's always a probability that they will spontaneously decay back into the ground state, right, from the higher level. And actually, when they do that, they release a photon. I'm going to draw a little wavy guy because photons are waves and particles. If we're really going to get into this, you don't need to know this, but if you really want to get into it, the symbol for a photon in chemistry and physics is a Greek gamma. So every time they transition from a high energy level to a low one, they emit a photon of a certain wavelength. And the wavelength of that photon depends exactly on how much energy difference there is between these energy levels. And so Bohr says, okay, so what's going on is that, say, this peak here, this big peak, is caused by photons in one particular higher energy state going down to one particular lower energy state inside that atom. And they're emitting that bluish photon. And in this atom we've drawn here, there are a couple different transitions. We could go from the highest, so I guess I'd call it n equals 3, down to n equals 2. That's one particular transition. You could also go from n equals 3 down to n equals 1. That's another transition. And you could also go from 2 to 1. So there's 1, 2, 3 different transitions you could have. So if we looked at what's called a spectrum, oops, that's a terrible axis. I'm going to draw it again. A spectrum of this theoretical atom that I've kind of made up. The intensity of light versus the wavelength. It might have, one peak here, maybe another peak here, and another one there. And who knows what the intensities of these three would be. It would be hard to figure out without knowing more. But it would have 3 transitions between energy levels. And based on which kind of atom it is, the wavelengths and the intensities of these energy levels is going to change. But every atom of the same type has the same transitions. And I should mention, too, the intensity, how much light comes out of each transition is relative to how many times that transition happens. And if you really want to get into it, this is some work Einstein did. There's probabilities for each energy level transition. And that corresponds to how intense each of them becomes. So that's all I want to say about that particular thing, because I first learned that in graduate school, and good Lord, there's no reason for anyone to know that in high school. But there's these things called Einstein A's and B's, which are coefficients that tell you how likely any given energy transition is. Anyway, that's a lot. But that's, I think, pretty important to know the interaction between light and matter. I guess I can also say, when a photon comes out, that means an electron dropped down to an lower energy level. If you send a photon into the atom, you can actually cause an electron in a low energy level to jump up to a higher energy level by absorbing that photon, which I think is pretty cool. So atoms can also absorb as well as emit light. All right, how we doing, guys? There's just one more thing I want to go over, and then we're gonna go hopefully a little early. I want to talk about the particles that make up atoms. So atomic. I guess they're technically subatomic particles because they make up atoms. And I've mentioned, I think, all of them so far, but just good to have a little bit of a catalog here. And really, I guess I would usually call this the particle zoo. So, first off, we mentioned the electron, which is a little e with a minus symbol up there. Anyone know anything about electrons? Anyone want to give us some information? What do you guys know about electrons? Say again? Did you say they have negative charge? Was that it? Okay. And we could ask the question, what in the world is charge? But that's a really deep philosophical kind of question. I'm trying to think of a really simple way to talk about it. Electric charge is essentially just how much electrical force something can exert on something else. Oof, that is a really weird way to put it. Okay, other properties of an electron: it has a very small mass, but it does have mass, and it appears to be a point particle. No size or shape. Also means it's indivisible. An electron does not appear, as far as we can tell, to be made up of anything else. It's just, that is what it is. So that means it's a fundamental particle, is what we would call it. Okay. And quite different to an electron is a proton. We're going to call it a p to the plus. Protons are positively charged. I'm sure I misspelled that. And actually, one of the nice things is that the amount of negative charge on an electron and positive charge on a proton is exactly equal. It's the same number, just this is minus and this is plus, which is kind of cool, I think. It's called the elementary charge, actually. Works for both of them. Relative to an electron, a proton has a very large mass, like hundreds of times. And a proton is not indivisible. It is made up of smaller particles. They're called quarks. There's a bunch of different types of quarks. Maybe I should talk about quarks a little bit. There are 6 types of quarks, actually. The vast majority of everything that we interact with, I'm not going to say the vast majority, literally everything we interact with is made up of, I'm going to make a little table. There are 3 levels of quarks and 2 parts. Okay. So the stuff, there's stuff that we interact with every day is made up of up and down quarks. There are also a different kind of quarks called top and bottom. Now, originally, before they were official, they were called truth and beauty quarks, which I think is way, like 1,000 times better than top and bottom quarks. I don't know why they got boring names and not truth and beauty. And then the last type is charm and strange, which did, for some reason, retain their wacky names. I think that every particle should have a wacky name like charm quark. You know? I just think it would make the world more interesting. We did get these at least, but we didn't get these. I don't know why. It's sad. Anyway, a proton is made up of 3 quarks. It's made up of 2 ups and a down. Whereas its partner particle in the nucleus, the neutron, which has a neutral charge, no charge, is made up of up, down, down. Yeah. So, a neutron also has a big mass. Almost the same as a proton. It's actually just a little bit more massive than a proton. So, those are the 3 major particles I wanted to talk about. Electron, proton, neutron. The electron exists in sort of this weird, undefined cloud around the nucleus. The protons and the neutrons exist inside the nucleus of the atom. Questions? Comments? Concerns? How we doing, everybody? From a scale of thumbs up to thumbs down, or anything in between, how we feeling? You know what? I will take a sideways thumb. I'm okay with that. It's the beginning of the year. It's a lot. All right, guys. Well, unless there's other questions, that's all I wanted to get through today. Was there anything else we wanted to talk about? So there's multiple ways. You can email me like a picture of your edits, or you can just type it out and email that to me. Either way. It is, remember, by the way, it's due next week. It's not due today. It's due Monday. Tuesday. Emiliano, you had a question too? Perfect. And Christian, I think you had emailed me about that. It's not due today, so you don't need an extension. Awesome. Anything else, anyone? All right. You're free to go. Have a great time.